yesterday we were looking at the stress concentration factor calculation for 3 of these points, basically the saddle point, quarter point and the crown point. And the combination, basically at the quarter point you will be combining by linearly interpolating between the points that they are in the vicinity. So, simple idea is, if you do not have equations, either you can develop a FE analysis yourself to find out what is the SCF, or you can use the existing empirical equations given by others to interpolate the stress concentration factor for these quarter points. It is a combination of, so basically it is a simple idea. Only thing is, we are not trying to find out the SCF value interpolated, we are trying to find out the stress range by multiplying the SCF with the corresponding stresses at each of these 3 locations. So, you will find the stress at this point and this point, and ultimately you are trying to find out the quarter point by simply adding, but this is only an example where all of them will be combined together, but you have to be little bit careful because there is a plus minus sign depending on the direction and the moment, the sign, you will see that this may be minus or plus. So, for example, if you want to write equation for all 8 points, you will have to rewrite this one for the quarter points in 4 forms, minus, plus and minus, plus, whereas the left and right, basically the crown point will only change the in plane moment, isn't it. For example, you have axial stress on the left side, if the bending moment is clockwise, you will see the right side is compressive stress, whereas the left side is tensile stress. That is why I have put the plus minus here. So, you have to be little bit careful in manipulating. So, there may be a question, you may be asked to basically plot the stress concentration factor or the stress range across one full chord interface. For example, something like this could be your bottom point, and then something like this. You may ask, plot at 8 points. So, that is your point where this bottom point, you go all the way on the left side and right side. So, you can plot the variation of stress concentration factor or the overall stress range. So, for a given problem you should be able to calculate nominal stress, which I think most of you are very familiar. If I give you applied axial load, applied bending moment in plane, applied bending moment out of plane, and you should be able to calculate F axial, F in plane, F out of plane, and then come back to the interface, you should be able to calculate the SCF values based on FTMU equations, which is available, and I will give you a printout. So, you can calculate, but you must remember the SCF values are given only for the 4 points, left, right, top and bottom. So, you should be able to calculate by interpolation and calculate the stresses and make a plot like what I have drawn in the blackboard. So, basically this is the idea to understand how you will do it. This typical joint, you can see fabricated joint, of course little bit blur here because of this, but otherwise clearly indicating multi-pass welding and gap available. So, you can see here in this particular location, though we have given 3 inches in this particular project, you end up actually having very small after the welding, because the weld has taken most part of the space available, and that is one of the area where you do not want to have weld overlap or weld on weld. This is the typical equation which I have just taken from API, actually reproduced in the appendix of the API. So, you can see here on the left side axially loaded chord ends fixed. So, you see here yesterday we were drawing one typical joint with boundary condition. So, instead of taking a large chord from one support to other support and middle loaded, this they have considered a small chord length, which is probably only the joint location, and ends are assumed to be fixed and basically loaded only by axial load. And the equation is given here for chord saddle, remember chord side and brace side, saddle point and crown point. So, that is all is given here. So, in if you go back to this picture, we have left side chord, left side crown, right side crown, and then bottom saddle and top saddle. Basically, there will be 2 saddle points and 2 crown points, both are going to be having same values. Only thing is, when you combine with your axial and bending stresses, you will see that you will be have to increase or decrease, because depending on the bending moment. So, basically you see here chord side and brace side. I have explained yesterday why there will be a different SEF. I think we have seen a stress variation from nominal stress to the footprint of the weld. I think we can go back to few pictures before, somewhere here. So, for the brace side we take the stress at the footprint of the weld here. For chord side we take the footprint of the weld toe at the chord connection. So, there will be a local area where which we have not simulated the weld, but the stress will be there. For example, if you go here, if you go inside here, the intersection between the vertical plate and the pipe, there will be a junction. We should not take the stress there, because we have not simulated the weld effect, and that is what the meaning that we want to say here is. Basically, stress concentration factor for chord is taken as the weld toe of the chord side, and for the brace is taken at the weld toe at the brace side. So, in between stresses we should not take. So, that is why you see a difference. So, you can see here the first, let us look at the chord saddle. The SEF depends on gamma value, which is basically the cylinderness of the chord, d by 2t, tau value basically the thickness ratio, and then the next parameter is beta, which is your d by d, the ratio of the diameter of the brace to chord, and then you have the angle, which is theta. Basically, these are the 4 parameters we discussed even for static capacity. Only the static capacity you may not have tau value there, but otherwise this is well known. These 4 parameters are going to influence the stress concentration factor. So, you can see all 4 of them are geometric parameter, how the joint looks. On the right hand side, you see here the short chord correction factor, basically, and the notation, the equation number is given just to identify equation number T1, T joint first equation, just on the right hand side you see here the correction factor F1, which we discussed yesterday. The longer the chord, you may actually see so you may have to calculate the stress concentration vector from this equation, multiply this by this F1. So, F1 equation for F1 is given at the end on the second page. So, you can see here it will be minimum 1 and can increase. So, basically can decrease depending on the geometric values. So, you can calculate the correction factor and use that after computing here, you multiply it. So, like this the whole set of 4 types of joints, 8 types of loading. So, see here axial load, and then the same T joint, instead of fixed both ends, have a spring supported basically ends. That means, this is going to be the realistic. If you look at the jacket, yesterday we were trying to draw one picture, you will never get a 100% fixity like this, because they are also connected to another member. So, you may have a stiffness which may prevent from rotation and translation, but it is not absolutely rigid. So, you may have a flexibility. So, you may have to consider that flexibility in here, and basically repeated for chord side, crown and saddle, brace side, saddle and crown. So, same equations modified and for different boundary conditions. So, if you go to the next, you will have a in plane bending, out of plane bending. So, now you see here we saw one simplified SCF table, very simple, alpha times A, 2/3 of A and 3/4 of A. A is a simple empirical coefficient to be calculated. So, that was the equation originally proposed several years back for simple joints. Now, after so much of studies, the equations for SCF has been elaborated so much. In fact, if you look at there was no differentiation between chord and saddle. So, let us go back to the table. If I just go back 1 minute, the simplified, if you look at here, there was only a difference between chord and brace, but there was no difference between a saddle point and the crown point. the stress concentration factor what was given here is just taken as one single value for brace side. Of course, at least there was a differentiation between the load types, axial load in plane, out of plane, but there was no difference between the saddle point and the crown point, which you could have seen from this picture obviously is not correct. If you look at this picture, obviously you can see from this FE analysis, the saddle point is going to be higher stresses, higher stress concentration compared to the crown point. So, that is what has happened over the years. More and more studies have been done and differentiation has been taking place. That is the idea behind why we do not want to use those old equations, which are simple, looking very easy to use, but then they are not reflecting the real picture, and that is why many more researchers have been involved in SCF calculations, experiments and FE analysis, finally come up with. So, this is one of the equation now after a very long deliberation. In fact, 10 years of deliberation by a research committee appointed by API since 1995 to 2005, they found that the equations given by FTMU still stand very good even after quite a large number of tests, large number of studies. The equations given by FTMU is still conservative compared to others. So, that is why we continue to use this, and it has been now part of API. So, we have to use it mandatorily. So, the first set of equation is for T joints, axially loaded, fully fixed condition. Second one is spring. The next one is the in plane and out of plane. Of course, the boundary condition does not really influence too great because of flexibility, and the correction factors and corresponding coefficients available are required for the calculation of end fixity parameter. Basically, typically C will be 0.7 means partially fixed. Most of the time you might remember in the tubular to tubular connections, if you have one tube on left side, right side and connect a cross tube, because of the flexibility, I think I tried to explain the other day in the for example, if you take one jacket leg during the member design, if you have one member connected this way, when you apply a loading, you can see here this wall thickness, this is a hollow section. Now, if this is solid, you actually can see here this rotation may not happen, but because this is not solid and there could be a local deformation which allows the rotation of this end, but it is not 100% rotation like a simply supported, because it is having its own stiffness. So, that is why we most of the time the tubular to tubular end connections we neither can consider as 100% fixity or 100% simply supported, it will be in between. You may rotate, but it may not allow full rotation. So, that is why this partial fixity. So, these parameters needs to be calculated according to the recommendation. So, 0.7 means typically it is about 70% fixed. If you go further down, you have axially loaded balanced X joints and similar equations for in plane bending, out of plane bending. Of course, sometimes you will see the equations are just repeated, that is why the numbers were given. The purpose for which the numbers in this order is given, because there will be a duplicated use. So, instead of rewriting, FTMA has just provided an idea of repeating, and then finally, you will have a K joint for axial load, unbalanced in plane bending, unbalanced out of plane bending, and then basically balanced axial load. So, several cases he has come up with after a long study and come up with these equations, which balanced out of plane bending, that means both the moments are similar or equal. So, you can see here these equations quite complicated, there is a potential of making mistakes. So, you have to be little bit careful. I will give you the better printout, because it is very hard to read in these slides because of reduction in size. Probably tomorrow I will bring the printout. So, you have to keep it in your hand throughout the course during the exam you can keep it. So that I think I have the original print. So, we can just print few copies to all of you, or I can give you the soft copy, you can go and print it. The next one is basically the SN curve. So, what we have done is we have the nominal stress calculated from a analysis of the structure, applying a wave height, wave period, and we have calculated the stress concentration factor. So, stress concentration factor multiplied by the nominal stress gives you the hotspot stress, and the stress range is defined as either twice or the difference between the maximum minimum. So, now we have a stress range applied, we also know what is the number of cycles that stress range is applied. So, we have the loading side, the demand side is known. Now, the capacity side we need to establish the relationship between number of cycles to failure at a particular stress range. So, that needs to be established. So, basically that relationship is called, so it is basically again demand and capacity. So, demand is established so far, and the capacity side is the allowable number of cycles, which is typically known as stress number of cycles relationship for a given type of joint depending on the material, connection geometry and weld profiling and the characteristics of material. So, basically this has been done to a great extent, I would say. In fact, many of these connections have been established. What we are just now looking at is a tubular connection. So, the SN curve is going to differ for each type of connection. If it is a tubular connection, something like this, there is a SN curve. If it is a plated connection, there is a different SN curve. If it is a plate to a tubular, will be another type of SN curve, because the relationship is going to be influenced by the type of connection, type of conditions that is being applied there. So, you see here few classes back we derived one relationship between the initial crack growth to final crack growth with a material constant, which is basically K1, which is, if you plot this relationship, the horizontal axis is number of cycles, the vertical axis is the range of stress applied, very similar to a problem of a paper clip. We know we were trying to do a simple experiment, basically opening the large angle is the higher stress induced at the junction. So, the larger the angle, the less number of cycles you need to break it up. So, you see here horizontal axis basically your number of cycles applied, then larger the number of cycles that you apply, the smaller the stress range that you require to break the connection, or if you go for a larger the stress or the effort, then you may break in the smaller number of cycles. That means, any number of combinations can actually fail the same joint, different combination of number of cycles and the stress range. That means, this statement here is correct. Basically, you may have numerous number of combination of number of cycles to stress range applied to produce the effect of same. For example, I want to produce 3 millimeter crack in a particular joint, I can have x number of cycles, y number of or y amount of stress range, or another combination that can exist with the slight modification to the stress and the number of cycles. So, that means, this constant depends on the material type, the connection type and also the welding profiles around the connection. So, that is why you see here, but of course, it is not almost linear, it is a non-linear curve, something like this typically you will see. Now, when you plot the same data in log axis or log plot paper, I think you might have seen in your mathematics course, normally you have a log paper just for convenience, and basically if you plot you may get. So, the characteristics have become so such that when you plot the SN curve in the log graph, it becomes linear. So, we can write this in terms of log equation. So, basically that is what we have done. So, you can see here the n is the number of cycles to failure, S is the stress amount or the magnitude, the range applied to the joint, and m is the slope of the linear or the straight line given there, and K1 is the constant depending on type of joint, geometry and associated effects. Remember, yesterday we were talking about SN curve includes undercut, the weld profiling and at the location of the weld toe. So, these effects are already included in here. So, depending on the type of joint, the K value or the K1 value, the reason why we do not want to use K, because K is normally used for other variables. So, that is why most of the references they use just K1, there is no grade fund, some of the codes they use K2. So, it depends on so not a worry, is a constant, that is what we wanted to use that. So, if you can actually rewrite this whole thing in terms of this, it will be very handy, because when you are solving problem you need to calculate the number of cycles given the stress range, because this is calculated from your previous analysis by applying loads, calculate the loads and stresses can be calculated, multiply by stress concentration factor, you get the stress range. So, you bring the stress range here and you know what is the K1 value for the particular type of joint and the slope is known. So, you can find out what is the number of cycles to failure. So, once you know this, then the fatigue problem is resolved. So, basically a typical SN curve. So, you need to remember every one of the SN curve developed by so many codes, it could be American code or it could be DNV code, all of them will be in this kind of form. Only what will differ is the coefficients, which is K1 will differ, M will differ. Sometimes you have a steep slope, the steeper the slope, this is not very good, because your stress range comes down. Flatter the slope is good, isn't it, because it will take a longer number of cycles before failure. So, that is the only difference. Sometimes you will see that instead of a single slope like this, some of the SN curves are having double slope, something like different slope for different ranges. You will see that steep slope, and then some of the materials exhibit double slope SN curve. So, again earlier revisions of API code, in fact, we were having single slope something like this. In the recent times, last 5 years, they have changed to double slope, because based on additional experimental studies. So, we will just see some of the examples. So, if you see here, another correction factor is given before we go to basically the various types of SN curves. So, what is the correction factor regarding? Basically, this correction factor is to incorporate the effect of scale. So, nobody knows what is the typical fabrication going to happen in future, but during the testing they have taken a certain amount of thickness and carried out the experiments for SN curve generation. Now, in future somebody is using higher thickness or lower thickness, it may actually not exactly reflect what was done in the experiments to generate this graph. So, that is called the thickness correction factor, scale effect factor, because in the real practice people are using different thicknesses, whereas the tests were carried out for reference thickness of 16 millimeter. Now, if I have a 25 millimeter thickness, the failure or the crack growth could be different than a 16 millimeter thickness. So, in order to account for the correction factor needs to be applied. So, the correction factor is very simple, the reference thickness is say 16 and your thickness is also 16, then it becomes 1, there is no correction required. As long as the thickness required or thickness used in your actual design is higher than this thickness, then the correction factor will always be higher than 1. So, basically you need to make sure. So, as long as you have ratio is 1 and basically the values of multiplication will come lower, but what you are actually going to get, you are going to actually use this one. So, that is why I have plotted, if you go to the next graph, I have plotted just as a reverse, because you will be using this S in your reading of the SN curve, not the other way. So, basically this is the calculated stress from your actual analysis and this is the stress range you are looking at. So, basically T by T ref. So, all your values, as long as your the ratio is 1, the multiplication factor is 1. If the ratio is less than 1, then you will see the values go as much as 101.8. So, the thickness, suppose you have 16, you have 30 mm or 32 mm and you will have the effect of that scale. So, that is why the stress range that you are going to use in your SN curve basically multiplied by 1.3 depending on what thickness you are using. So, this correction can increase the stress concentration factor, basically that is not included in the stress concentration factor. So, it is included in the SN curve. So, whenever you are reading the SN curve, before you go and apply your S value, you correct the S value by using this, that will be always greater than 1 if your thickness is higher. Various types of SN curve available, you can see here 4 organizations I have just listed down, all of them almost have all 4 joint types. American Code, both the earlier version and the recent version, and the DNV and the ISO. All of them, just now if you look at the recent ones, almost the curves are similar, but the earlier version of the API has a single slope curve, which we have used to call it X and X prime, whereas now they call it W and WJ, WJ improved, and basically DNVs they call it T, basically welded tubular, and the ISOs they just notation is TJ, does not matter, almost they reflect every similar idea, only the notation is given slightly different. If you look at other connections, instead of tubular, if it is a T plated connection, they will have P as a SN curve, just a notation. What we are interested is these values, the basically the values of log K1 or K1. Sometime you will find instead of giving log K1, you will be directly given K1 value. So, you have to find out what is the log K1 value depending on which code. Almost all the DNV codes are giving directly the values of K1, whereas the API they just give log K1. So, you have to be little bit careful in using it, and the earlier version of API you can see here 13 and 15, slope is 3.74, 4.38, whereas the new version you can see here slight change 12.48, 16, and the slope has been differentiated between the steep slope to gentle slope for demarcation between n 10 to the power 7 cycles. So, basically you will see in the graph, and then the DNV curve not a major difference. You will see that if you compare this with this 12.48 versus 11.76 and 16 versus 15, slightly conservative, the DNV curve is slightly conservative. So, if you see the comparison between all this, just to get an idea what exactly is happening, for example, if you look at this pink color, it is basically the improved hammer peening, that means you hammer it on the weld. I think we did discuss, or maybe we will be discussing this improvement techniques later on. Basically to improve the welded joint, we try to remove the rough material, number 1, profile it, and a lot of activities can be performed on the weld, so that the stress concentration can bring down. So, that is the idea. So, if you see here there are 3 of the methods to improve. You can see the higher you go, higher the stress range it can take. Higher the stress range it can take means the fatigue life will be higher. So, that is the idea behind. So, if you compare the previous revision of X prime curve versus the WJ, WJ is the green color, somewhere here it is hidden there, and the X prime curve is just above. So, you can see here the blue line little bit above here, and the new one is basically this little green, almost coinciding everywhere except it is extended little bit, and you can see the new curve is slightly lower. Of course, it is very difficult to see here, but when you actually enlarge, it could produce reasonably conservative results. That is why that is one, and there was no double line. The original one was single line versus the double line. Probably I think you need to enlarge it. So, basically for computation purpose, either you will be given these values, you do not need to memorize, or you will be given the charts like this. For example, in the examination point, if I give you a chart, you should be able to read the chart, because you know what is the stress range that you have. So, you go to the graph, you go to this point, and then straight away come down, you will be able to read what is the number of cycles that the joint will fail. So, basically to read it, or if you are given the this type of numbers, the type of SN curve will be given, and a table will be given with all the SN curve K1 values or log K1 values, and you should be able to calculate using this equation. A generic equation like this will be given, or you can convert that yourself into typically just anti-lock. So, the purpose of SN curve has to be clearly understood, is to get the relationship between the stress range and the cycles to failure, and different type of joint, different type of SN curve exist. Just you have to keep in mind there are several types of joints. I have not introduced here, I have just introduced only the tubular connections. So, if you go to DNV curve, you will have 20 different SN curves for different types of plated connection. Like if you go to ship construction, you will see a plenty of different joints. There you will have to select the suitable SN curve applicable to your joint. If it is a fillet welded, it is a different SN curve. If it is a penetration weld with a stiffener, is a different SN curve. So, you have to go and select it suitably. Fortunately, for tubular connections, it has been so generalized that any type of connection, does not matter whether it is a T connection, Y connection, X connection, does not matter, it is only a single SN curve. Life has become little bit easier to select. Only thing is, you will find slight difference between the previous revision of API and the present revision of API. So, we have to use only the present revision, which is just basically the 21st edition with a correction supplement, which is called WJ and improved WJ. So, what is improved WJ? Basically, the weld is smoothened. I think the other day we were trying to discuss about, probably we have a bit more discussion, how you will be able to improve a profile of the weld by simply doing hammer work, or you may actually grind it, so that the joining of the weld with the parent material is very smooth, means the stress concentration is reduced. This is another example taken from DNV C203, which is basically a recommended practice for fatigue analysis of the structures specifically, and basically tubular connections. I have just picked up one of the graph. You can see almost similar. If you just overplot this on this, you will see that it is almost both of them are copied, except very small difference. And there is actually two lines shown here, seawater with corrosion protection. So, the tubular joints underwater also protected against corrosion, has a slight lower stress range compared to the same joint if it is in air, that means above water. So, basically that is the idea behind. So, how do we get the calculations for the fatigue damage? So, we have come up with the steps now. Last 4 classes we have been discussing about fatigue, starting with crack propagation theory and basically Paris law of crack growth, relationship between crack growth and the material constant or material toughness, and then we have learned about so called stress concentration factor, which typical equation from FT mu was shown to you, calculation at 8 points. So, stress concentration factor multiplied by nominal stress is giving you the stress range. Then you have gone to SN curve to read the number of cycles to failure. Prior to that, we also have the idea of the number of cycles applied due to external waves on the structure. So, what we know is 4 variables. We have number of cycles applied, is not it? Stress, which is basically this, you can call it stress range, hotspot stress range. So, these 2 values, this is coming from your analysis, SCF value, analysis is done by you, SCF is given by SCF equations, parametric equations from the code, number of cycles, allowable cycles to failure, or you can say number of cycles to failure, that will be better, number of cycles to failure. So, we have number of cycles applied, number of cycles that the joint will fail corresponding to that stress, is not it. So, basically 4 parameters define the demand and the capacity. So, demand side is number of cycles and basically the stress applied, this is on the demand side, and basically on the capacity side, number of cycles that the joint may fail. So, you have this, but of course, is related to this one, the cycles applied. So, remember in the whole picture of the tubular joint, for a design life of 25 years, you are not going to have only one value of S, one value of N. You may have several combinations of S values and N values corresponding N values of. So, basically what will happen is you may have N1, S1 and N1 corresponding. So, you may actually repeat and correspondingly, because that many waves. So, basically T1 and correspondingly you will have, this is your defined C state, which you have it from your scatter data, measured or simulated, or somehow you have got the data from the site that each wave height, wave period, corresponding number of cycles. From these 2-3 values you have calculated the S value, because you have done the analysis and you have calculated the SCF. After that you have gone to number of cycles to failure. So, once you have this information, now we can just sit back and see what exactly is going to happen. Every time a particular stress value is applied on the structural joint and a damage is done. The damage is hypothetically given as the ratio of number of cycles applied to number of cycles that the joint may fail. So, that ratio, for example, if a joint is going to fail at 1 million cycle and applied cycle is also 1 million, then the damage is 1, and basically cumulatively add, because as we know very well, the fatigue is a phenomena which can start from X and propagate over the period of time, and basically that is why we have to keep on add the effect, and nothing but is the equation described here is going to be, the fatigue damage is nothing but N1 divided by N1 plus N2 divided by N2 until all the data or all the waves in that particular field is added together, which is called Palmgren-Miner's rule, because he proposed this several years back, can't remember the date, but 30-40 years back he proposed this idea, and seems to be well working, because 100% we use this idea to design the offshore structures for fatigue. And one difference, just what I have done here, typically API requires minimum 8 directions. So, that means for a given structure, whether it is a floating structure or fixed structure, you look at 8 directions for the C state conditions. For a rectangular structure, 8 directions means 4 orthogonal, 4 diagonal simply. For a ship also similar, you will have 2 end on, 2 beam side, and then 4 quartering C. So, basically you have to look at those conditions and get the information. Each direction you have to find out what could be the potential wave period, wave height, and then basically the number of cycles, and then carry out the analysis. So, that means this 1 to n 1 to k is nothing but as many number of waves that you may have in that direction. We saw one wave scattering table, one big table, you have got certain combination of waves and wave period, wave heights and wave period. So, each one will become one case, and as long as you are fully filled, then you have more number of cases too. And remember, these calculations needs to be done at 8 points on the interface. Remember, we have left, right, bottom, top, and then 4 quartering points. So, quite a lot of computation needs to be carried out. So, only difference is you are not going to add cumulatively the results of 8 points. Each point will be monitored separately. You understand the idea now? Whereas, you will be adding the cumulatively all the C states, you will be adding it, whereas the each point on that peripheral interface between the brace and the card, each one is one problem. Do not go and add all the damages in all 8 points, they are individual hotspot locations. So, you have to look at them. So, do not have to add it, but if you are intelligent enough, you do not need to do all 8 points, you can figure out which point may actually create more problem for fatigue calculation. So, you can only do calculation for that particular point. Suppose if you know, but if you do not know, what we need to do is we need to repeat this calculation for all the 8 points, whichever gives you the highest damage, that will be the representative design for that joint. You understand the idea, no? Whereas, for each joint you have to do the calculation for all the C states, all 8 directions, add them cumulatively. Now, how many things we have discussed? We have discussed from C state, scatter data, deterministic wave, spectral wave. So, you could see the direction, number of cycles, there is potentially large amount of uncertainty involved, because of the data is not available, and data is going to be actually used by the designers for future purpose, but the available data is only the past, and it could be longer term data or it could be shorter term data. So, what we are going to have lot of assumptions made for extrapolation purpose of next 20 years, next 30 years, next 50 years. So, there is a reasonable amount of uncertainty on the demand side. That means there could be, it could exceed or it could be lower than that. If it is lower than that, nobody is worried, because joint is not going to fail for sure. It may be over design, but then we can be happy, but if it exceeds, the joint is going to definitely fail. So, as usual, we need to have a factor of safety on the damage what you have calculated here. That means, we can allow theoretically to 1, the ratio can become 1, but we cannot allow, because we need a safety factor, and that is typically like in the member design we had a factor of safety of 1 point, how much, 1.67, is not it. So, typically here you see here in this table we have a factor of safety of minimum 2, that was we have been using this factor of safety of 2 for many years as suggested by API, but in the recent times studies indicate that the scattering of the scatter data, you know, basically the amount of information available to the designers is quite limited, because nobody wants to spend time and money in measuring wave at a particular site, what they normally use the mathematical simulation. But then, as you know very well, mathematical simulation has got serious limitations, and that is why you have to apply higher factor safeties. That is one of the reasons, but the other reasons you can see here, inspectable, not possible to inspect. That means, if you see a jacket 100 meter water depth, people can dive. I think if you have gone for scuba diving, you know, without any assisting equipments, you can dive probably for 10 meter, 15 meter, 20 meter, but after that you may not be able to go down. But with special equipments, you can reach as much as 50 meter, but beyond which even those equipments may not be able to take, you may actually need a compression chamber. So, when you have such requirements, inspection becomes too expensive, maybe sometimes not feasible. So, that is why we call it possible to inspect or may not be able to inspect. The reason why we need to see this inspection, because the fatigue damage is cumulative. For example, if you go for a 5 years plan, every 5 year we will go down and look at the joint, whether any crack or any propagation or any initiation, because you remember the threshold, until the threshold is reached, the joint is not going to show any failure. Only the threshold is reached, then starts opening up and you can see. So, every 5 years if you have a plan to go and look at it, if there is a problem, you can do 2 things. You can actually prevent the joint structure from failing by doing a repair on the structural connection, or you can shut down the platform, not use it, to avoid human loss. So, 2 things you can do, and that is why this inspection is very important in terms of fatigue evaluation. So, we need to define what period of inspection you would like to do. So, in order to do that, if it is possible to inspect by means basically possible by the owner, this is left to the designer and owners, because if you go to a company like Cell, they may have all possibilities of equipments and facilities to do inspection. If you come to some other company, they may not have, they do not have anything to inspect, they may have limitations. So, that is why if you do not want to do inspection, if you do not have means of inspection, go for a higher factor of safety, but if you can do inspection every time, every year, then you can reduce, the risk is reduced. So, that is why inspection possible, inspection not possible, and failure critical and non critical. So, what if you cannot inspect, if the joint fails, if it is a secondary joint, does not make the structure to collapse, that needs to be decided by the designer. Designer knows which joint is critical joint. So, he can identify whichever joint is very critical, apply a higher factor of safety. So, that is the idea behind this simple matrix, which is normally applied to almost all jackets, and you can see at the lower end of the matrix, which is 2. So, that means you need a minimum factor safety of 2, and as much as you can go to 10.